So welcome to another advanced higher chemistry video. This is going to be the first video looking at transition metals, which is one of the largest topics within inorganic chemistry. So there'll be a few videos breaking down the various aspects of transition metals. This is just going to be our introduction. So remember that transition metals are that block of metals in the middle of the periodic table. They are also known as the D block, and they are called the D block because their outermost electrons are found within D orbitals. The other thing that makes them transition metals is that they can have different oxidation states, so they can have ions of different charges. So we know this, we know iron can be iron 2 or iron 3. You know that chromium could be the dichromate or the chromium 3+, and manganese can be permanganate or manganese 2+. There's lots of different possibilities, and in future videos we'll look at how to work out oxidation state and charge on a transition metal. But what you need to know is that the electrons in transition metals are always in the D blocks, and they can form ions that have partially filled D orbitals. So that final definition, they can form ions with incomplete or partially filled D orbitals, means that not every D block element is technically a transition metal. For example, zinc, because zinc always has 10 electrons in the D orbitals, therefore it does not have partially filled D orbitals, so it is not a transition metal even though it is part of the D block. So there is a slight variation in definition. They're not exactly the same thing. Now, when it comes to filling electrons into the D orbitals, you will mostly only be asked for showing the 4s and the 3d orbitals in either spectroscopic notation, as you went over in a previous video, or the orbital box notation, which is what I'm going to show you here, and how it varies across the 10 first row transition metals, or first row D block elements, if I'm going to be more exact. So scandium is the first element in the D block, so it has its two 4s electrons. Do not forget the 4s electrons, and then we have one electron in the D orbitals. Titanium, second, very easy. Vanadium, 3. Chromium is where it gets, remember, awkward. It gets this variation because chromium we would expect it to have 4 in the 3d orbital, but if it takes an electron from the s orbital and puts it in the 3d orbital, you can end up with that nice stable half-filled d orbital. So that's what happens. You have one 4s electron and 5 3d electrons. Manganese goes back to the normal pattern, 2 4s electrons, 5 3d electrons. Iron, nickel and cobalt just go as normal. You start pairing up electrons within the d orbitals. Copper, again, it's one of the exceptions to the rule like chromium, where it's going to take one of the electrons from the 4s orbital so that it can completely fill the 3d orbital. And then zinc has all the 4s and the 3d electrons completely, orbitals completely filled with electrons. So you do need to be really, really, really careful when it comes to chromium and copper. You also need to be careful that you're following Hund's rule, so that the first 5 atoms within, first 5 elements within the D block, you're filling the D orbitals individually, and you're only starting to pair them up after the 5 orbitals have all had 1 electron in them. Now, transition metal ions, and this is what gives transition metals their transitional quality, is because they can usually form ions of different charges. They are metals, so they are always going to form positive ions. They do this by going from the element and losing electrons. Loss of electrons is oxidation. And so we can say that transition metals of different charges have different oxidation states. They have been oxidized to different degrees. And we're going to have a video about oxidation states coming up. Really important rule is that when transition metals become ions, they lose the 4s electrons first. So any transition metal ion that is 2+, copper 2+, cobalt 2+, iron 2+, vanadium 2+, those 2 electrons that were lost are always the 4s electrons. The d electrons are always touched last. Okay, so you lose the 4s electrons first. Now there is a little bit of contention between which of these orbitals, the 4s or the 3d orbitals, is higher in energy. The fact that you lose the electrons from the 4s orbital before you lose the electrons in the 3d orbital would indicate that the 4s orbitals are higher in energy, therefore easier to remove. But if you look at the filling pattern, the 4s orbital fills before the 3d orbital, so it's not a strict, completely well understood part of chemistry. So it is unclear under the Aufbau principle which should come first, 3d or 4s. So you are not marked wrong if you write the 4s before the 3d or the 3d before the 4s. I would stick to using how it comes across in the periodic table, putting the 4s before the 3d. Just remember that the 4s electrons are lost first. So if we look, for example, at vanadium, and using the noble gas notation for ease, but vanadium would be argon, and then the 4s2 3d3. You could also get away with saying that it's argon 3d3 4s2. When we go to the vanadium ions, the vanadium 2+ ions, you could represent this as argon 4s0 3d3 or argon 3d3 4s0. However, the best way is actually to remove any orbital that doesn't have any electrons in it, and you would just write argon 3d3. So that has been a quite brief introduction to transition metals and what it means to be a transition metal, how to fill the electrons in orbital box notation, and which electrons are removed when a transition metal forms an ion. In the next lesson, we'll look more about different oxidation states and how we can work out the oxidation states of transition metals.